Good evening, students. How are you all? So, welcome to the fourth session of real numbers. I'm Kanika ma'am, your mathematics teacher. So, last week we had started with real numbers, and then we completed the same thing. But today also we'll give some more time to real numbers. So, it's a revision class of real numbers where we'll be revising the previous concepts which I've taught you last week. Also, we'll be practicing a few questions. So let's quickly start with the revision part. Real numbers is defined as the set of rationals and irrational numbers. So children, as discussed earlier, we have a set of rational numbers, the numbers which can be written in P by Q form, and then we have set of irrational numbers which cannot be written in P by Q form. Now together, when we combine irrational and irrational numbers, they become a set of new collection, that is real numbers. So real numbers include all the numbers such as minus 2 by 5, minus 2, 0, 1. These are all rational numbers. They're real numbers as well. And we have irrational numbers like root 3 pi. They're also real numbers. Now children, in the previous week we had discussed Euclid's division lemma also. Given two positive integers a and b, there exist unique positive integers q and r satisfying a equal to bq plus r, where 0 less than equal to r less than b. So as discussed earlier, if we have two numbers, let's say 2 and 9, and if we divide 9 by 2, we are going to get 4 as the quotient, we'll get 8 here, and then 1 as the remainder. So this is actually dividend is equal to divisor into quotient plus remainder. So this is your dividend. This is your divisor, then this is the quotient, and this is the remainder. So Euclid's division lemma says when we have two positive integers a and b, and when we take the bigger out of these a and b, like here we have 9 bigger than 2, if I divide the bigger one from the smaller one, I'll get a quotient and the remainder, which can be written as dividend is equal to divisor into quotient plus remainder. So this also we discussed earlier. Now coming to the next concept of fundamental theorem of arithmetic. Every composite number can be expressed or factorized as product of primes, and this factorization is unique apart from the order in which the prime factors occur. Like this means that if we have a composite number, let's say we have 18, we can prime factorize this and we can write this as product of 3, 3 and 2. Now this prime factorization is unique. This means that 18 can be written as product of 3, 3 and 2. We cannot write it as product of 2 into 5. That will not come out to be 18. We cannot write it as 5 into 7. That will also not come out to be 18. So the prime factors are unique. So it has to be 3, 3 and 2. But the order in which the prime factors occur, they can vary. We can change the order. We can write this as 2 into 3 into 3. Or 3 into 2 into 2. We can change the order, but the prime factors will remain the same. Okay, now coming to the next concept. Here we have for any two positive integers a and b, HCF of two numbers a and b into LCM of two numbers a and b is same as the product of a and b. So when we have two numbers 26 and 91, we are going to first write them as product of their primes. So we have 26 as 2 into 13, 91 as 7 into 13. Now the HCF of 26 and 91, as we can see, 13 is a common factor. So the HCF here is 13 and the LCM is 2 into 7 into 13, that is 182. Now if we take the HCF and the LCM and we multiply them, we are going to get 2366, 2366. Also, if we take the original numbers, the numbers which we took right in the beginning, 26 and 91, then also the product will come out to be 2366. So from here we can conclude that if we have HCF of two numbers and we have LCM of those two numbers and we multiply them, we will get the product same as product of the given numbers. Now we've also discussed the decimal expansion in the previous class. Now decimal expansion means when we have a number, a rational number, let's say the rational number, we know it can be written in P by Q form. It has two cases, whether it has terminating decimal expansion or it has non-terminating repeating decimal expansion. So this we did in class 9 also. A rational number has either a terminating decimal expansion or non-terminating repeating decimal expansion. Also, if we have a number having non-terminating, non-repeating decimal expansion, then it is an irrational number. So we know for the case of terminating decimal expansion, it's a rational number. For the case of non-terminating repeating decimal expansion, it's again a rational number. So if I have a number in P by Q form, which is a rational number, how am I going to figure out whether it has a terminating decimal expansion or a non-terminating repeating decimal expansion? So let's see. We'll study this in the next concept. So this also we discussed last week. Let x equal to P by Q be a rational number such that the prime factorization of Q, that's the denominator, is of the form 2 raised n, 5 raised m, where n and m are non-negative integers. Then x has decimal expansion which terminates. So we have example here, 13 upon 3125. Now this particular theorem means if you have a rational number and then you take the denominator for this P by Q. P by Q, rational number can be written as P by Q form. So the Q, if we take, that's the denominator here, and we prime factorize it. If we get the prime factors either as 2 or 5 or both and nothing else except that. I'm repeating myself. We get the prime factors either as 2 or 5 or both and nothing else except that, then we can say that the decimal expansion of that number terminates. Like in this case, we have 13 upon 3125. We can prime factorize the denominator and write it as 5 into 5 into 5 into 5 into 5. So this is 5, we are multiplying by itself 5 times. So then the decimal expansion terminates. In this case, it has a terminating decimal expansion. Now let us discuss the next theorem. Now again, if we have a rational number written in P by Q form and we take the denominator Q and we prime factorize it. If the prime factorization of Q is not of the form 2 raised n, 5 raised m, that means the denominator has prime factors even if it has 2, 5 or both, but then it has something else except that. So whether it has 2 or 5, that doesn't matter, but if at all we have a prime factor other than 2 and 5, then we can say that the decimal expansion of that number is non-terminating repeating. For example, here we have 64 upon 455. We can prime factorize this and we can write this as 5 into 7 into 13. Now we have 5, but then we have 7 and 13. So as I told you earlier, we should have 2 or 5 or both. That doesn't matter in this case, but then if at all we have something else except 2 or 5, like in this case we have 7 and 13, then we are going to say that the decimal expansion is non-terminating repeating. So in order to check whether a rational number has terminating decimal expansion or non-terminating repeating decimal expansion, we are going to take the denominator, we will prime factorize it, and once we prime factorize, we'll look for the prime factors. We will observe the prime factors. If the prime factors are 2 or 5 or both and nothing else except that, then we will say that the decimal expansion terminates. And if we have 2, 5 or both, or even if we don't have 2 or 5 or both, but then we have something else except that, then we will say the decimal expansion is non-terminating repeating. I hope children you've understood till here. Now coming to the next concept, which we discussed on Friday also, but then still I'm going to discuss this again. Now let P be a prime number. So this is one of the theorems which is given in NCERT, and here only the theorem, the statement is required, the proof is not required. This statement we'll be using to prove the next concept. So let P be a prime number if P divides A square, then P divides A, where A is a positive integer. This means if we have a prime number, let's say 2, and we know 2 divides 10 square. What is 10 square? It's 100. We know that 2 divides 100, then 2 divides 10 also. So if we have a prime number 2, if 2 divides 10 square, then 2 divides 10 also. Now, this concept we'll be using to prove that the square root of all the prime numbers are irrational. Like we have square root of 2, it's an irrational number. Square root of 3 is an irrational number. Square root of 5 is an irrational number. And square root of all the prime numbers, they are irrationals. So, children, in the previous class, we had discussed in detail that square root of 2 is a prime number. Now, we are going to do in a similar way. Let's say that we're going to take square root of 3. Square root of 3 is an irrational number. So, we'll be doing this question. Given that square root of 3 is irrational, hence prove that 2 plus root 3 upon 5 is an irrational number. Children, please notice in this question, this is one of the questions of CBSE. It's given that square root of 3 is irrational. So in this question, it is already given to you that square root of 3 is irrational, and you have to prove that 2 plus root 3 upon 5 is irrational. Now what if this is not given to you? You have been asked to prove first that square root of 3 is irrational, and then you have to prove that 2 plus root 3 upon 5 or any other expression related to root 3 is irrational. So we first prove root 3 is irrational. So I hope you remember this. Whenever we come across such questions, the first step is let, if possible, root 3 be a rational number. Root 3 be a rational number. Now children, if root 3 is a rational number, then we can write root 3 in the form of a upon b, where a and b are co-prime. A and b are co-prime. This means they have only one common factor, that is 1. Nothing else except that. They have only 1 as the common factor. So where A and B are co-prime, this is something very, very important to write, because this we'll be using to get contradiction in the end. Also, B is non-zero. B is non-zero because B is denominator. Denominator can never be 0. So here we are going to start with let, if possible, root 3 be a rational number. Then we can write root 3 in the form of A and B, where A and B are co-prime numbers. So if they're co-prime numbers, that means this is in the standard form. Now in the next step, we'll take this B on the other side, and this will get multiplied. So we'll get B root 3 is equal to A. Now in the next step, we are going to square both the sides. So we have B square into 3 is equal to A square. 3 we are going to take on the other side. This will get divided. So we will get B square is equal to A square upon 3. Now please notice A square upon 3 is giving me a positive integer. So we can say that A square is divisible by 3. So we can say 3 divides A square. Now this 3 is a prime number, it's P. It divides A square, so it is going to divide A as well. So we'll write here 3 divides A. Now if 3 divides A, we can write A as 3 times of C. Let us take that C is some integer. C is some integer, so we can take it as any integer. Children, I am repeating this. If 3 divides A, then A can be written as 3 times of C. Now in the next step, we are going to square both the sides. So we'll get A square is equal to 9C square. Now, please notice here, I'll name this as equation 1. A square is equal to 3B square. A square is equal to 9C square. So equation 1 and 2, they are both giving us values of A. This is equal to A square, and A square is also equal to 9C square. So from the first and the second equation, we can say that 3B square is equal to 9C square. And then we can cancel out this. This is 1 time and this is 3 time. We will get B square is equal to 3C square. In the next step, we are going to take this 3 on the other side and it will get divided. So we will get B square upon 3 is equal to C square. From here, we can see that if we are dividing B square by 3, we are getting a positive integer. So we can say that 3 divides B square. Now if 3 divides B square, we can say that 3 divides B also. 3 divides B. Now please observe, 3 divides A and 3 divides B. So we can say that 3 is a common factor of A and B. 3 is a common factor of A and B. Now if 3 is a common factor of A and B, this contradicts that A and B are co-prime. Right in the beginning, we took A and B as co-prime numbers. That means we said that A and B, they have only one as the common factor, nothing else except that. But now we are saying that 3 is a common factor of A and B. So this is a contradiction. This is a contradiction. That means our assumption was wrong. And what was our assumption? We assumed that root 3 is a rational number. So that's a wrong statement. So we'll write here. Therefore, our assumption was wrong. So our assumption was that root 3 is a rational number. That's a wrong statement. So if root 3 is not a rational number, it has to be an irrational number. So thus we can say root 3 is an irrational number. Now children, in the same way, you can prove it for any prime number. Square root of all the prime numbers, they are irrational numbers. So this you can prove for all the prime numbers. Square root of 5, square root of 7, anything you can do. So children, I am repeating this entire theorem again. Please be very, very attentive. So we had to prove that root 3 is an irrational number. Now we've started with let if possible root 3 be a rational number. Now if root 3 is a rational number, it can be written in the form of A upon B, where A and B are co-prime numbers. Co-prime means that they don't have any common factor other than 1. Also, we have taken B not equal to 0. B is non-zero because B is in the denominator. Division by 0 is not possible. Now we'll take this B on the other side and we will get B root 3 equal to A. In the next step, we are going to square both the sides. So we'll get B square into 3 equal to A square. Now this 3 we are going to take on the other side. We are going to get A square upon 3. Now A square we are dividing by 3 and we are getting one integer here. So we can say that A square is divisible by 3. Now if 3 divides A square, then 3 divides A also. So we've just started this. If we have a prime number P, if it divides A square, it is going to divide A also. In this case also 3 is a prime number. 3 divides A square, so 3 divides A also. Now if 3 divides A, we can say A is equal to 3C. A can be written as 3 times of some integer. Now next step we've got by squaring both the sides. So we have A square equal to 9C square. Now in the first question, in this equation we have A square is equal to 3B square. And here we have A square equal to 9C square. So from first and second equation, we can say that this 3B square and 9C square, they are both equal. So we have taken 3B square equal to 9C square. 3 and 9 will get cancelled and we will get B square equal to 3C square. 3 we are going to take on the other side and we will get B square upon 3 equal to C square. Now this shows that if we have B square, we are dividing by 3, we are getting a positive integer. So 3 divides B square. B square is divisible by 3. Now 3 being a prime number divides B square. So we can say 3 divides B also. Now here we have 3 divides B and here we have 3 divides A. So 3 is a common factor of A and B. 3 we have got as a common factor of A and B. But then right in the beginning we said A and B are co-prime numbers. That means they have only one as the common factor. No, nothing else except that. But then here we are saying 3 is a common factor of A and B. So this gives us a contradiction. Therefore, our assumption right in the beginning which we took, root 3 is a rational number. Our assumption was wrong. And finally, we can conclude that root 3 is an irrational number. I hope children you have all understood this. Now the second part of the question is that we have to prove 2 plus root 3 upon 5 is an irrational number. So this is also similar to what we did just now. We have to prove that this is an irrational number. We are going to start like this. Let, if possible, 2 plus root 3 upon 5 is a rational number. Now, if it's a rational number, we can write this in the form of a upon b, and b we are going to take non-zero. Now, we'll take this b on the other side and this 5 on the other side. So, actually, we are cross multiplying. So, this is b times of 2 plus root 3. In fact, even if we don't take this b here, it would be convenient. I'll show you why. Wait a minute. So what I'm going to do here, I'm only taking this 5 on the other side. I'm giving you an easy method. I'm taking this 5 on the other side. This will get multiplied. We'll get 2 plus root 3 is equal to 5a upon b. Please notice, children, here, one term at a time we are going to take from the left hand side and we are going to take it to the right hand side. Only root 3 will be left here. I'll show you how. Now 5 I've taken on the other side, so I've got 5a upon b. 2 I'm going to take on the other side, and this will become 5a upon b minus 2. Now I'm going to take the LCM here. So I will get 5a minus 2b upon b. Now as we can see, this is in the form of p by q. So we can say that this is a rational number. Now this is a rational number and this is equal to root 3. So we can say that root 3 is also a rational number. But that's not correct. It's wrong. Root 3, we have just proved that it's an irrational number. So how can we say that a rational number is equal to an irrational number? Not possible. Therefore, our assumption which we took in the beginning, that 2 plus root 3 upon 5 is a rational number, it's a wrong statement. This is wrong. 2 plus root 3 upon 5 is rational, is a wrong statement. Finally, we can say 2 plus root 3 upon 5 is an irrational number. So, all such questions, how we are going to proceed with the same? One at a time, we are going to take the terms on the right hand side and we should be left with only the square root term. Like if you have square root 2, square root 3, square root 7, whatever you have, only this should be left here. Okay, children, I hope you've understood this. Now, let us discuss some other questions. We are going to discuss some practice questions. So, before we do that, I'm going to discuss some questions based on this concept. That how we figure out whether a rational number has a terminating decimal expansion or non-terminating repeating decimal expansion. Now in this question, we have to state whether 6 upon 200 has a terminating or non-terminating decimal expansion. So I'm going to take this 200, that's the denominator, and I'm going to prime factorize this. So this, we are going to start with 2, we'll get 100 here. Then we are going to start with 2, we are going to get 50 here. Then we'll start, then we're going to proceed with 2 again, 25. Just see, they're all divisible by 2. Finally, we'll have 5, 5, 5 and 1. So we can write this 200 as 2 into 2 into 2 into 5 into 5. So 6 upon 200, we can write it as 6 upon 2. If I'm multiplying by itself 3 times, I'll get 2 cube. And this is 5 square. So this is of the form 2 raised n, 5 raised n. Here the prime factors we have 2 and 5 both, and please notice nothing else except that. So we can say that 6 upon 200, it has a terminating decimal expansion. It has a terminating decimal expansion. Have you all understood, children? Okay, great. Now what type of decimal expansion does 29 upon 2 square into 5 into 7 have? Very simple here. You don't even need to prime factorize the denominator. It is already done for you. As we can see here, in the prime factors, we have 2, we have 5, but then we have 7 also. So here, just by looking at the 7, you can conclude that it has non-terminating repeating decimal expansion. Non-terminating repeating decimal expansion. Okay. So this one is a bit different. After how many places will the decimal expansion of 189 upon 125 will terminate? Okay. Now in this case, we have 125 here. they're not asking us that whether it is terminating or non-terminating. They're asking after how many places will the decimal expansion of 189 over 125 will terminate. So what I'm going to do, I'm going to multiply both numerator and denominator by 8. So what is the reason behind multiplying it by 8? I want to make this 1000. So if I'm multiplying this by 8, I need to multiply this also by 8. I cannot multiply it by some other number, or I cannot just leave it as it is. I hope you remember this. You've done this in grade 6 also. Okay, so 125 into 8 will give us 1000 and 189 into 8 will give us 1512. Now 1512 over 1000. Very clearly we can see it can be written as 1.512. It has 3 zeros here, so we are going to write it as 1.512. Finally, we can conclude that after 3 decimal places, this decimal expansion will terminate. So we can create a lot of questions like this also. Now, let us discuss this question. Show that 8 raised to the power n cannot end with digit 0 for any natural number n. So children, a similar question, we did this in NCERT also in the previous class. We have 8 raised to the power n. Please notice we have to check whether it ends with digit 0. Now, if a number ends with digit 0, that means it has 0 in the ones place. If it has 0 in the ones place, then we can say 10 is a factor of that number. So if 10 is a factor of a particular number, we can say that 2 and 5, they are also prime factors of that particular number. I'm repeating myself. If 0 is there in the ones place of any number, then we can say that 10 is a factor of that number. Now, if 10 is a factor of that number, then 2 and 5, they're also the prime factors of that number. 2 and 5 both have to be there. So let us now prime factorize this. We can write this 8 as 2 into 2 into 2 raised to the power n, and this can be written as 2 raised n into 2 raised n into 2 raised n. Okay, so we can write this as 2 raised to the power 3n also. Now please notice it is very clear that we have 2 as a factor of 8 raised n, but then we don't have 5. 5 is not there. So 8 raised to the power n will not have 10 as a factor. Finally, we can conclude that 8 raised to the power n cannot end with digit 0. That means it cannot have 0 in the ones place. So you will get a lot of questions like this also, where you have 8, like here you have 8 raised n, you can get to it for 12 raised n, 6 raised n, 4 raised n. Such questions also you can get in the exam. Now we have to show that 2 into 3 into 7 into 13 into 17 plus 13 is a composite number. So before we begin with this question, I want to clarify what is the difference between a prime number and a composite number. This we've done in grade 6 also. So prime numbers are those numbers which have only 2 factors, 1 and the number itself. So all the numbers, in fact, they have 2 factors, 1 and the number itself. For prime numbers specifically, they have only 2 factors, not 3 factors. Only 2 factors. That means they come in the table of 1 and they come in their own table. Like we have 5. 5 has factor 1 and 5 and nothing else except that. So it has only 2 factors. Now composite numbers are those numbers which are not prime numbers. That means which do not have 2 factors. They're more than 2 factors. Like if we say 8. 8 has factor 1 and the number itself, that's 8. Also it has factor 2. 4 is also a factor of 8. So it has more than 2 factors, as we can see. So a number which is not prime is a composite number, or say a number having more than 2 factors is a composite number. Now there are 2 ways of solving this question. Either you multiply this entire thing, then add 13 and then you prime factorize it and then you say that it is more than 2 factors. But that's a tedious method. As we can see, this is given in the form of the expression where we have this 13. This is the common thing. I'm going to take out this 13 and then I will have 2 into 3 into 7 into 17 plus 1. So in this number, we can very clearly see that it can be written as 13 times of something. So if it is 13 times of something, it is very clear that 13 is a factor of this number. So this number has factor 1, has factor the number itself, and has another factor that is 13. So we are able to prove that it has more than 2 factors. Like we can say that it has 3 factors, maybe more than 3 also. But it has more than 2 factors. We are getting 13 as the third factor here. So finally, we can say that it's a composite number as it has more than 2 factors. I hope you've all understood this. Now we have to express 0.2317 in the form of P upon Q, where P and Q are co-prime, and also express Q in the form of 2 raised n into 5 raised n. We have to express this in the form of P and Q. Now please notice 2317 we have, and we have to express this in the form of P by Q. You can just straight away write this as divided by 1000. Very easy. 2317 divided by 1000, 10,000 we have. 10,000 because there are 4 digits after the decimal. That is why I've written here 10,000. Now we want P and Q to be co-prime. It is very clear this is an odd number and this is an even number. The co-prime numbers we cannot cancel further. It's not possible to cancel, so they're co-prime numbers. Now we have to express this in the form of 2 raised n, 5 raised n. That means this Q has to be expressed. That means we have to prime factorize this denominator. So we have here 10,000. We're going to divide by 2. We'll get here 5,000. Then by 2, we'll get 2,500. Again by 2. Just see, these are all even numbers. That's why I'm straight away dividing by 2. So I'll get 1,250. Then by 2, I'm going to get 625. Then by 5, then I'm going to get 125. Then by 5, I'm going to get 25 here. Then by 5, 5, 5 and 1. So I can write this 10,000 as 2 raised to the power 4. Just see, there are 4 2's here. 2 raised to the power 4. And here we have 4 5's here. So times 5 raised to the power 4. So now I've expressed Q, that's the denominator 10,000, in the form of 2 raised n into 5 raised n. I have expressed 10,000 as 2 raised 4 into 5 raised 4. Now, this question, this is given in NCERT. There is a circular path around a sports field. Sonia takes 18 minutes to drive 1 round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So this question means that we have a circular path, and then we have 2 people. We have Sonia and then we have Ravi. Sonia takes 18 minutes to take 1 full round. Let's say that, Sonia starts from here and she takes 18 minutes to take 1 full round, and Ravi takes 12 minutes for the same. Now suppose they both start at the same point and at the same time. So if Sonia is starting from here, Ravi will also start from here. So they're both starting from this particular point and they're taking rounds here. So after how many minutes will they meet again at the starting point? So Sonia is going to take the first round in 18 minutes. She's going to reach here. Then she's going to take another round. That's how she's going to complete 36 minutes, because 18 minutes for the first round and 18 plus 18 minutes for the second round. So two rounds and all. That's 36 minutes. In the same way, Ravi takes 12 minutes for the same round. So he completes 1 round in 12 minutes. The second round he's going to complete in another 12 minutes. That means he's going to take 24 minutes and all. And the third round in 36 minutes. Like this, we can figure out that actually 18 and 12 we have to take and we have to solve for the LCM. So these numbers are very small. We can do it like this also. For 18, we can list the multiples. We have 18, then we have 36. And for 12, we have 12, 24 and 36. So we can say that 36 is the least common multiple in this case. So Sonia and Ravi, they are going to meet again after 36 minutes. So either you can just list the multiples here, since these are very small numbers, so we could do that. Otherwise, you can just take the LCM using the prime factorization method. So you can divide by 2, you will get here 9. Then we have here 6. Divide by 2, you will get your 9. And then we have 3 here. Then by 3, we're going to get 3 here. And then 1, 3, 1, 1. So now when you multiply all of these, you're going to get the LCM. So we have LCM as 2 into 2 into 3 into 3. This is actually 36. So after 36 minutes, Sonia and Ravi, they are going to meet again. So the answer is 36 minutes. Okay. I hope you've all understood this. Okay. All right. Now let us discuss one more question. Now we have two positive integers P and Q. P is expressed as a square b cube and Q is expressed as a cube b. And we already know that a and b are prime numbers. So already we have P and Q as positive integers and we have been given the prime factorization of P and Q. They're already expressed as the product of the prime numbers, of their prime factors. We have to verify that LCM of these two numbers multiplied by HCF of these two numbers is same as the product of the numbers. So please notice this is one of the CBSE questions. So I'm writing here P is a square into b cube and Q is a cube into b. Now as we can see that the HCF here is, we have a square here and a cube here. So we can say in HCF we have a square. We have b cube here and then we have b here. So we have b in the HCF. So HCF of these two numbers, we have a square b. Now let's talk about LCM. We have a square and then we have a cube. We are going to take the factor with the highest power here. So we have a cube here. And then we have b cube and b. So we can write here b cube. So finally the LCM is a cube b cube. Now LCM into HCF we are going to take as a cube b cube times a square b. So this can be written as a cube into a square, that is a raised to the power 5. Then we have b cube into b, that is b raised to the power 4. We have b raised to the power 4. Now let us take the product of these two numbers. So we have p into q, that is a square b cube times a cube b. So a square into a cube will give us a raised to the power 5. B cube into b will give us b raised to the power 4. So now we know that the LCM of two numbers is same as product of the numbers. Finally, we have verified this. I hope students, you have understood this question. Now, we'll discuss one more question since we have time. Okay. Now let us discuss this one. Show that root 3 plus root 5 is an irrational number. Now, root 3 plus root 5, before we start with anything else, we are going to first of all expand this. We can write this as a plus b whole square, which is actually a square plus b square plus 2ab. So in this case, it is root 3 square plus root 5 square plus 2 into root 3 into root 5. So this is 3 plus 5 plus 2 root 15. Now we can combine this and we can write this as 8 plus 2 root 15. So finally, root 3 plus root 5 square is actually 8 plus 2 root 15. Now this 8 plus 2 root 15 we have to now prove that it is an irrational number. Now it's an irrational number, so we are going to do it right from the beginning. Let if possible that this is a rational number. So if this is a rational number, it can be written in a by b form. And then we are going to take 8 on the other side. So we've discussed this today. So this will become a upon b minus 8. Now we are going to take the LCM here. So we have 2 root 15 is equal to a upon b minus 8. Once we take the LCM here, on the right hand side, we'll get a minus 8b upon b. And 2 we are going to take on the other side. So we have a minus 8b upon 2b. This is in the form of p by q. So we can say that this is a rational number. This is rational, but then this is irrational. How can we say that a rational number and irrational number, they are both same? Not possible. Finally, we can say that our assumption that 8 plus 2 root 15 is equal to a by b, that means it's a rational number, it's wrong. So finally, we can say 8 plus 2 root 15 is an irrational number, or we can also say, we can write this in the form of root 3 plus root 5 square. So actually, this is equal to root 3 plus root 5 square. So root 3 plus root 5 square whole square is an irrational number. Okay, children, we have discussed a lot of questions today. I hope you've understood the concept. That's all for today. Thank you, children.